sure, just follow if you're not sure what to do when you're getting a buffet, just follow whatever the person who's in front of you, you know? So, what we're going to do, Markus Land.
And also, the free lunch means one plate once, no refill, and if you want to drink or a sandwich, you're going to pay for that. Okay? There were some misunderstandings during previous ones.
It just comes from common sense, okay? So, yeah, without further ado, Markus Land will give his first lecture on
Grothendieck theory. Okay, hello. Thanks a lot for having me. It's a great pleasure to be back in Copenhagen. I don't know, I miss this place a lot. It's so good to be here. So let me do the absolute shitty move and do this. Yeah. This is just a plan. You could have all read the abstract and you're fine. Okay? So plan for the talks is the following thing. For now, R is a commutative ring and epsilon is plus or minus 1. Nothing else will matter, but the theory is more general, but this is the only thing that matters. For now, what we care about is this commutative monoid in the infinity category of spaces, and just for the sake of familiarity, I write that still as spaces, not as infinity, sense, substance, or anima, but that's all the same thing. So, unimodular forms over a ring, by that I mean you work with finitely generated projective modules. Okay, better? You work with finitely generated. I was about to say I do the Stefan move, and it's like okay. So you work with unimodular forms of finitely generated projective modules. That means you have a map from P tensor P to R, say, that is maybe symmetric or a quadratic form. And you're allowed to think about these things in the most naive way that you care. And such forms, together with their isomorphisms and the orthogonal direct sum, form a symmetric homology groupoid, which we're allowed to view as a commutative monoid in this infinity category of spaces. So space is grouped with a coherent multiplication, commutative multiplication, and the Grothendieck space of R is just its group completion. So on pi 0 we group complete these isomorphism classes, and on higher homology groups this is some sort of refinement of the group homology of these isometry groups. Okay, and the goal for the first 3 lectures is to say something about this space and to indicate how it relates to something like manifolds or so. I mean, I'm sorry, this is the only thing I have to offer, so this is what we'll do. So first lecture today will be just the general setup of concrete categories. So what we'll do is we'll set up a general categorical language, which will help us treat this object. And then in the second lecture, and maybe the beginning of the third, the plan is to describe this space for the integers in all the 4 variants. So epsilon b plus minus 1, or q and s, and we'll focus on the symmetric case first and then move on. The intention for the third talk is to do some applications of it to the stable cohomology of, say, the symplectic group over the integers. So the group of isometries of the form of the surface. And other applications to signatures of certain bundles over stably frame manifolds. That's just sort of some fun calculations you can do if you understand this space, and so I thought I'd present that. And the plan for the final talk would be to discuss a bit the fact that there are spaces that satisfy complementarity called PD complexes, and you can wonder, are they actually manifolds or not, or what variant are they? And, okay, there's some L-theoretic and Grothendieck style interpretation of the situation, and I'd just like to tell you how our formalism allows you to treat these objects. Okay, so without further ado, let me just give the basic definition of the object we care about. Yes, and I should also say, of course, I mean, always feel free to interrupt me. I have made plans to do something, but if you have different plans, I don't care. I mean, you're allowed to change my plan. I don't mind about that. And so what I chose to do is I chose to act as if you all know what a stable infinity category is, and then I act as if you don't know what a concrete category is. So that's where I'll start. And feel free to ask me anything or anyone else in the break or afterwards or also during the lectures if you're unfamiliar with something. But that's just the choice I made. I'll make some examples that are the most important ones to keep in mind for these lectures, and we can see where to go from here. Okay, so an admission category, it consists of a pair, which I write C comma, where C is a small stable infinity category, and because I say infinity all the time, I did it exactly once, and I'll stop doing it now, probably. So this is a small stable category, and copper is a countervariant functor from this opposite, or from C, to the category spectra, which is reduced and too excisive in the sense of good Lie calculus. So I'll recall in a moment what these things mean. So reduced just means that a stable category has a preferred zero object. I call it 0. Spectra is one stable category, so it makes sense to ask that about 0, 0. And too excisive is something I'll say in a moment, but in particular, you can do the following. If you have any functor that's reduced, you can look at its value on x plus y, and you can find out that it spits out at least copper of x plus copper of y as a direct summand. And then there's a further term that you just call b copper of xy, some functor that depends on two variables. And so b copper is now a functor from C op times C op to spectra. And you just require, too excisive. It's a slightly stronger statement than saying that this functor is bi-exact. It's exact in each variable. It sends fiber sequences in each of these variables to fiber sequences. And just to tell you a bit better what happens, so we get maps of the following kind. I can take this linear term and evaluate it on x and x. So that seems to be a direct summand in copper of x plus x. And because copper is a covariant functor, I claim that I can restrict along the diagonal and I get a map to copper of x. And in the same manner, I can use the fact that x plus x maps to x by the fold map, the identity on each side, so I also get a map to bxx. But now x plus x, the diagonal and the fold map, these are equivariant for the flip action of x plus x. So it turns out that b copper of x, that's a symmetric functor in the two variables. If I flip the two terms, okay, I have to flip here, but x plus y is y plus x. So this is a symmetric functor, and these maps are equivariant, so really they factor through the C2 orbits and the C2 fixed points on both sides. And it's a fact that you just have to believe me that this map is the only map that you think ought to exist, namely the norm map, which is informally given by summing up, that you take a point, and you sum up its point with the C2 action on it. Now that's going to be equivariant, so it lands in the fixed points, and then also factors through orbits. That's the norm map. And really, too excisiveness can be interpreted as saying that the cofiber of this map, I'll call lambda of copper, and that this functor is exact. That's this is equivalent now to say too excisiveness. Given the fact that the B is already bi-exact. And okay, this is equivalent to this other definition of too excisive in terms of sending strongly three co-partition cubes to three partition cubes or so. So if you're familiar with this, that's good, and if not, it doesn't really matter. Okay, now the norm map is a map that exists, and its cofiber has a name, it's called the Tate construction. Okay, so let's just call it like this. And what we observe is that, by definition, now you get a full vector diagram of this sort. And it's a fact that any reduced to excisive functor is canonically decomposed into such full vectors. So this is the so-called linear approximation of this functor, and this is the symmetric cross effect. And any such functor can be written in this manner, sort of in a functorial way. And so this might or might not show up later when we discuss how to write down particular examples. So far it's not too important. It's just, okay. So a Hermitian functor from C comma to C prime comma prime consists also of something, a data called f and eta, where f is a functor from C to C prime, and eta is a natural transformation from comma to f, the comma star of comma prime. Okay, so I'm sort of maybe not being super great, maybe I should write f of star. But I mean, roughly speaking, is comma is a functor from C to spectra, contravariant, and comma prime is one from C prime, so I can precompose with f. I get two such functors, and I can have a map. That's what I call a Hermitian functor, going between them. And so that describes a category I call cut H, the category of Hermitian categories. These objects are emission categories and functors are emission functors. And they compose in sort of the only way you could imagine. So you say that C copper is called Poincare. If there exists a functor that you call D copper, I guess what's the natural way it should go? Maybe it should go from C up to C, such that you can do the following. You think of D copper as a functor from C up to exact functors from C up to spectra. Yes, that's what you get from the fact that it's bi-exact. So this is an exact functor from C up to here, and C sits inside here by being an A-line embedding. So that takes an object from here to the spectrum of mass blank X. Okay, so that's a fully faithful embedding, and in particular this functor either factors through C or not. And I claim it ought to factor through a functor of this kind, which happens to be an equivalence. That's what you call something Poincare. That's a property of a Hermitian category. Either it is Poincare or not. It's not a property of a category to be Hermitian. You have to give the structure. Okay, that's what it is. And likewise, a Hermitian functor, maybe I'll be brief here, between Poincare categories.
It's a little bit difficult to see when you write in this catalog.
Yeah, I agree. Hermitian functor is, I won't erase it, sorry. Between Poincare categories is Poincare. Yeah, I think I'll do it from now. So a Hermitian functor is Poincare if a canonically associated map from F dual to dual prime F. Let's see if this makes sense. So F is a functor from C to C prime. The duality is something that is on C prime. So that's something that makes sense. It's a functor from C to C prime. This is also a functor from C to C prime, maybe off or so. And you ask if this map is an equivalence, and the exercise that I think makes sense to think about is that this map is induced, evaluated on an object X, is induced by the identity of the dual of X. Okay, now you can try to make sense out of that. So take this identity, it's a point in the space of maps from dx to dx, and then you can try to map that space of maps to a space of maps from here to here. Okay, so I invite you to try to do that, and if it doesn't work, then let me know. Here? Yes, a Hermitian functor, f, eta, between Poincare categories is Poincare if an associated map that intertwines f with the dualities is an equivalence. So a Hermitian functor gives you a preferred way of comparing the duality in C with that of C prime via f, and you call it the functor Poincare if that canonical comparison map is an isomorphism. So it actually intertwines the dualities. Okay, and this notion leads to a category of Poincare categories. As with objects Poincare categories and morphisms Poincare functors. So that's a subcategory in the technical sense of cut H, but it's not full. So objects are restricted and morphisms are also restricted. Okay, so let me write it comes with a sort of forgetful functor to cut H. Okay, so let me give examples. The most important example is if R is a commutative ring. Then per of R, it's some stable infinity category, but you can think about it as taking finite chain complexes or bounded chain complexes of finitely generated projectives and inverted quasi-isomorphisms. So, one thing. You can also think about it as saying you take all chain complexes and invert quasi-isomorphisms and then specify some subcategories, the things that are generated under co-limits in the infinity category in the sense from R. But I think for today it's maybe intuitive to think about the objects in there being chain complexes of finitely generated projectives up to quasi-isomorphism. Okay, and then you can consider the functor that I'll call copper x quadratic on an object x. And what you do is a simple thing. You just do the thing that you think you do in this business of forms. at maps from x tensor Rx to R. Okay, so this term comes with a C2H by flipping x and x, because x tensor x is equivalent to x tensor x. And R also comes with a C2H, mainly given by multiplication with epsilon. Epsilon is plus minus 1 or something. Maybe I should call this sub epsilon R. So here we act by multiplication with epsilon. So that gives a conjugation action on this mapping space, and you take C2 orbits with respect to this action. And maybe, yes, okay, so I'll write it like this. And you can do the same thing and take fix points instead. Okay, and so there are two exercises. Is that E comma, okay, and for one, there is this famous norm map that still exists. It maps from orbits to fixed points, and the norm map identifies both of these bilinear functors you get, and they're given by the functor that can send x, y to map R x tensor R, y to R. Okay. Just so you can just take it out. What comes out if you stick in x plus y and x plus y. Okay, so this is what you get, and so this implies that these comma epsilon quadratic and epsilon symmetric of R and these are Poincare structures on curve R with duality G comma xt maps from x to R. This is just what comes out. It's the natural thing we would think. So if you just know from plain algebra this unimodular forms over projective modules, the formula would be you take norms over R from P tensor Rp to R, and you take actual fixed points or actual orbits, and that would represent symmetric forms or quadratic forms. And then you just do the homology theoretic analog of that. Just do everything derived and take homology C2 fixed points or homology C2 orbits. So here's an important proposition in this business, namely, you can look at the category of reduced and two excisive functors on curve R up to spectra. So an object in here is a candidate for a comma. Yes? And you can do something. So I said that this category, you're allowed to think about it as chain complexes or projectives, and in particular, it comes with a functor from projective modules. That sort of takes a projective and views it as a chain complex sitting in exactly 1 degree. You can restrict any reduced to excisive functor to projective modules. And, well, what you obtain is still a functor that's reduced, so setting 0 to 0 still makes perfect sense. Being too excisive doesn't really make sense anymore. Projective modules don't have a notion of fiber sequences, but what still makes sense is to be so-called too additive. I just want to have suggestive notation. Other people call this too polynomial. It's just the condition that I put on this board. It's just saying that this cross effect is bi-additive. That's something that makes perfect sense once you have a projective modules. Okay, so that you can restrict and you obtain an object in here, and the statement is this is an equivalence of categories. Yeah, that's a kind of a non-abelian tone theorem. Essentially, where this comes from. Okay, so that says if I want to understand candidates for these Poincare structures on perfect complexes, really I only have to understand what happens on projective modules. And taking this into account, I invite you to think about evaluating these objects on projective modules. Let's think about what do I get? What is this thing if I stick in a projective module? And in particular, think about what is the pi 0 of this mapping space, and when is the mapping space actually discrete? Can this happen? Is it actually really true or not? And I invite you to think about examples where it's the case, or other examples where it's not the case. Okay, so that's something you can do. And then you can do something more. Because I talk about two additive things, I never need spectra to be stable here, right? Because I'm just talking about functors and 0 to 0 and some other things being bi-exact, bi-additive. So I can look at functors that are reduced and two additive that happen to take the values in the Lie groups So here I view an abelian group as a spectrum via the Einberg-MacLane space factor. So that takes any abelian group to the Einberg-MacLane spectrum. That's exactly one homology group given by that group in degree 0. And it just turns out that Schlichting observed is that this category is just equivalently described by what are called form parameters. So just in case you know about forms in ordinary algebra, Mach has this notion of form parameters on projective modules over rings, and this condition is a slight generalization of Mach's thing. But in some sense, I think it's maybe instructive to think about form parameters as some abstract gadget, which you can think about reduced in two additive factors. It's just some formal way of producing from a projective module and a Beery group of whatever your favorite type of form is. And then this proposition tells you that this uniquely sort of gives you a permission structure on perfect complexes in this big category. Okay, so that's something you can do. And I say it because that's going to be relevant for us. So in particular, let me say sending P to Hom over R, P tensor R, P R epsilon actual, or maybe I should do orbits, and Hom over R, P tensor R, P R, C2 fixed points. So here by Hom I really just mean Hom in the ordinary category of abelian groups. I just actually take this actual R module of Homs and take C2 orbits for the same C2 action that I had before, and the fixed points, the actual subdivision of fixed points. And then it's again an exercise similar to this exercise, that this is in fact reduced and two additive. Okay. So these uniquely give rise to commas, so give via proposition rise to something we call comma genuine quadratic epsilon or epsilon genuine symmetric. Genuine is a bad name, I apologize for it. It's just supposed to say that this is something purely homotopy theoretic. You just take this object with a C2 action and you just take C2 fixed points or orbits in the homotopy theoretic sense. And this is something that's trying to be closer to algebra. On a projective module, it's supposed to give you exactly what you want and not something that whose pi 0 is the correct thing. So spoiling your exercise before. Turns out that for a projective module, this pi 0 and this pi 0 is the right thing. But it has more homology groups and this one doesn't. It's a different, a priori different structure that's more closely related to the algebra that you might care about, that I care about. Okay, so if R to S is a map of commutative rings, then the claim is the factor that extends scalars is sending a projective module over R to a projective over S and then doing it on chain complexes or on perfect complexes. So this extent or this refines to a Poincare factor for comma epsilon genuine, or maybe I put it in this epsilon quadratic, epsilon genuine quadratic, epsilon genuine symmetric, epsilon symmetric, and same for S. Okay, so what I'm saying is that the map of commutative rings also is compatible with these structures I write down. I get Poincare functors on the level of perfect complexes with these types of forms attached to it.
It's a little bit difficult to see all your superscript.
So it's difficult to see what?
Don't write any smaller.
Okay, I'm supposed to write bigger. Okay, I can do that. Yes, okay, so here's another example. Consider the category of finite spectra. So in other words, that like just in terms of getting notation, right, that's just the perfect complexes over the sphere spectrum instead of over some compact ring. And then I can write down a Poincare structure using this this description as follows. Call it comma u of x, and I'll define it by a pulled x square, saying I'll take the ordinary spanner Whitehead dual of x, so d is just maps over the sphere length to the sphere, and something like dx h c2 dx take c2, and this map is what's called the take but be happy to explain more about it. If you don't know this, it's not too important. I'm just trying to say that there's something you can write down that's sort of homotopy theoretically. It's just God given there. You do the sort of most naive thing you could imagine. But it's sort of not trivial to explain this in detail. I don't want to do it now. I just wanted to say it for those of you who understand it's good, and for those of you who don't, come to me in the break and then we'll discuss it. U because it's universal. That's another exercise I maybe say in words. So whenever you have here's a fun fact. We'll come to it, but you can look at reduced and 2 excisive functors from finite spectra to spectra, and that has an evaluation on the sphere functor to spectra, and that functor happens to be co-representable by this comma U, so it's U for universal. The universal thing. We'll come back to this. Okay, so that gives a number of examples of Poincare structures you can write down, and sort of in algebra, ones that are homotopy theoretic in nature, and ones that are slightly more algebraic in nature, with these derived functors of actual forms. And these constructions are compatible with morphisms of commutative rings. If you have a map of commutative rings, then extensions of scalars refined to Poincare functors for any of these 4 variants. Yeah. The fun fact says this is co-representable by comma U. This leads to something we'll see later, but I cannot make sense of that statement just yet. In fact, I need to do the exact next definition. So namely, I mean, that's all good and fine. I set up some general blah blah. There's some categories with some structure, but I do care about these objects, and I care about basic invariants of these Poincare categories or Hermitian categories. And the basic invariants are what are called Poincare objects that satisfy Poincare duality. This is what these categories are trying to axiomatize. That we're allowed to say that an object satisfies Poincare duality. So let me try to explain that. Okay, so a Hermitian object in a given Hermitian category C, comma, consists of a pair. Maybe I call that pair X, Q, where X is an object in C, and Q is a point in the underlying infinite loop space, or in the underlying space of the spectrum of X. So we think of comma of X as the spectrum of forms on X. Axiomatized what forms mean by saying comma of X. And so I take a point in it. In other words, I take a form. Okay? And so that makes sense. And it's if C comma is Poincare, then we say XQ is Poincare if an associated map that I call Q sharp that goes from X to the comma dual of X is an equivalence. And okay, so maybe this time I don't let you do the exercise yourself, I just try to do it myself. See if that works. So if I want to understand this space of maps from X to T of X, then I can use the definition of a Poincare category to say I unravel what this means. That B factors through a duality as a middle functor. That unravels precisely to saying that this spectrum of maps is equivalent to BXX. This is just what it means. And then I can do something that I've already told you. I can map comma of X to BXXH2, and I can forget fixed ones. I mean, I told you I have this composite, and I claimed it refined to the correct map. So I have this composite, and Q is an element in here, and I just call the associate element in here T sharp. Yes. So any form gives rise to a map from X to its dual, as you're supposed to be familiar with from algebra. Form is maybe a map from P tensor R, P to R. You can adjoin over, I get a map from R to the dual of R. And you call an object Poincare if this associated map from X to its dual is an equivalence. So that's the analog of a unimodular form, so to say. Yes, maybe the examples are less important. Good. Yes, maybe one thing I can also say in words. It's the other construction you can do. Imagine you have two Hermitian objects, xq and x prime q prime. Then you can add x and x prime, and you can try to add q and q prime. So I invite you to do that, and I invite you to then work out that if you add two things that are Poincare, the sum is also Poincare. Okay. So on the set of Poincare, or on this space of Poincare objects, I have a natural sum operation. Okay. And the observation, which is related to the fun fact, it's related to, is that we obtain functors, spaces, maybe this is something I call Herm. So what I want to say is, like, if I give myself the Hermitian category, I can look at the collection of all objects equipped with a form of it, and that comes with the canonical notion of morphisms. I can just say that the one form restricts along the map I have to the other form. And so I get a category of forms that I call Herm for some good reason. And if I take the underlying space of the category, so I just neglect all non-invertible morphisms, then this is often referred to as the space of forms for a given category, and the claim is this is a functor. And the related thing to the fun fact is that it's not any functor, it's a functor that's co-represented by this category. The finite spectrum of this universal thing. So it's not any functor, it's in fact a co-representative functor. But maybe that's not too important now. And for cat B, so if you have Poincare objects, that only gives a space. The notion of having a unimodular form doesn't play well with just arbitrary maps. Something that's well defined under isomorphisms, but I don't really want to say that a unimodular form receives a map from another unimodular form by a zero map or something. It's just not something that's reasonably well defined. So here I take C comma to the collection of all x q, Poincare objects. And likewise here, take it to the collection of Hermitian objects. Okay, so we have functors of this kind. Yes. Okay, questions about these basic definitions so far? As I want to make one more definition that relates to this notion of Poincare objects, and then make a couple of examples. Yes, I mean, these are, so this guy is co-represented, they're co-represented by the same thing. Yes, that has to do with the fact that giving a Hermitian form is the same thing as giving a Hermitian functor from finite spectra with comma u to your favorite thing. And then that functor can or cannot be Poincare, as that Hermitian object can or cannot be Poincare. These two notions just, I mean, they correspond to each other. Right? So a form on xq is the same thing as giving a Hermitian structure on, maybe with xq is a form in cq. And then there's a unique functor from finite spectra to the C, sending the sphere to x. That's this idea that finite spectra are built with a unique exact functor from finite spectra to C. This is just because finite spectra are built under finite coordinates from the sphere, so if you say where the sphere goes, you know where everything goes. So there's a unique functor of this sort, and then giving Q of x. Okay, now I can wonder what that is. that's the same thing as this. So by definition, this is Q of, well, maybe I call this function pi x of the sphere. Is that right? And so now that's a. Now we use this unfact. I'll let you work this out for yourself, or we talk about it later in the discussion. The sum fact that evaluating on the sphere can be described in terms of mapping on this universe. This is more like, you just have to sit down and work through the definitions. It's not something that's very insightful. I think if I try to do it now, and do a bad job at it. But roughly speaking, the statement is giving a Hermitian form is just the same thing as mapping from this category to here, so refining this functor to a Hermitian functor. And then the question whether or not this functor is Poincare is just the same question as to say whether this Hermitian object is Poincare. Just how it comes out. So, okay. Good. So, yeah, those are the most important objects that we care about, our Poincare objects. I have given myself this notion of a Poincare category, and then I can talk about objects equipped with a form that's unimodular. Yes? I have the collection of such objects that forms a space that comes with an addition. And I need more information than that. I also need to now axiomatize the notion of a cohomology. So now things are going to become a bit more geometric. If you're familiar with this, so a cohomology between Poincare objects. And so x prime q prime and x q consists of, on the one hand side, a span like this in C. So it's some other object that maps to x prime and x. And let me say in words. The example in a moment will be if you have an actual cohomology of manifolds, then what we'll be allowed to do is apply cochains to it. Cochains is contravariant, and that's why the arrows go in the wrong direction. So geometrically, a cohomology, of course, has the boundary mapping in, and not the other way, but it has to do with the fact that we do things with cohomology rather than homology. Just a choice we made. I apologize for it, but that's we have to live with it now. So this is a span in C, and then I need to give myself an element in the value of kappa on x prime and on x, and I take the fiber product over W. So concretely that means maybe I give this map a name f prime and this map a name f, and then I can pull back q along f, and I can pull back q prime along f prime, and both of these things are now points in kappa of W, and I give myself a path in the space omega infinity of kappa of W from the one to the other. Yes, so again, the cohomology consists of the native of the W mapping to both things, and the witness that the restricted folds are equal of W. And okay, but that's not yet all. You still have to have some non-degeneracy condition, and the non-degeneracy condition is as follows, such that the square that I write down. So what can we do if we have these things? We can start with W and map to x and x prime via our maps f and f prime. And now we can observe that f and f prime are both Poincare objects. So they are canonically identified with their duals. Yes? And then I can play the game in the other direction. Now I restrict along my map f and f prime. So I get two maps to D of W. And again, it's an unraveling of definitions that this equality tells you precisely that this diagram computes. Okay, this is sort of how it comes out. This data gives you a witness of the fact that this diagram computes. And so, once you have a commutative diagram, you're allowed to ask whether or not it's a full vector. So you do ask that. And okay, I'll write down the example that comes from manifolds, and then you know what this means. Essentially, this encodes Lefschetz duality for manifolds with boundaries. And one way you can read it is saying this diagram is the full vector if the two vertical fibers are isomorphic. And then we'll work this out in a moment. It says something like relative homology is going to be something like relative cohomology. example, here you read this object as x prime, and here you read this object as dx. The final p is going to be some relative cohomology or relative homology. This is what it is. Okay, so that's what a cohomology is. And maybe I'll say it in words as you're used to. A cohomology is the same thing as, between these two things. The cohomology is going, it ought to be the same thing as a null cohomology between the direct sum of that and the changed orientation. And an orientation changeable is something that makes perfect sense because we're allowed to do minus. If you have a form, then you're allowed to put minus in front of it, you get a new form, and that sort of corresponds to changing the orientation in geometry. And so it's maybe a fun fact or a fun exercise to work out that a cohomology in this sense is the same thing as giving a cohomology from 0 to x plus x prime minus. As you're used to. And null cohomologies in our world are called Lagrangians, because that's what it is in algebra. I'll work this out now. Okay. So, I acknowledge that this is a lot of definitions to take in if you haven't seen them, but I invite you to focus really on the notion of concrete objects in a category and the notion of the cohomology between concrete objects, because we're going to use this to define the Grothendieck space and the L-theory space tomorrow and work with it, almost exclusively on an informal level, define objects by talking about concrete objects and cohomologies, essentially almost exclusively. Okay. Now it seems that I have not lost my finger. Okay, so examples. So P is a projective finitely generated module over R, and maybe you have some lambda form where lambda is, quadratic, symmetric, whatever you think, any sort of kind of form that you have in mind. Then you can take P, Q inside Hermitian objects, or maybe I should call it forms, for R with respect to this genuine lambda. Yes, so I just don't want to write quadratic symmetric all the time. Just pick your favorite kind of form, and then I told you there's this nice monobilian derived functor, and its value on projective modules is just exactly where this lambda form lives, and so you can just take that and you get a form. No, yes, thank you. I need that, thank you. Yes, thanks. And if this is unimodular in the algebraic sense, then you will upgrade this form to a concrete object. That's the point of unimodularity. It corresponds exactly to the forms that are concrete objects, not only forms. Okay, and for instance, L inside P is a null cohomology, or Lagrangian, as we call it. So that it is sounds like a bad thing, but so you do the following thing. So maybe now you have a Q and you restrict it to L, and that ought to be 0. So you have a form, and then your form ought to vanish on the Lagrangian. That's usually what's referred to L being isotropic, and then you want to have a maximality condition for such an isotropic thing. And the way you work it out is you look at what the definition is to get an null cohomology. Okay, so let's check what is the condition for an null cohomology. Well, this is 0. Here's L, here's P. So now I need to give myself this point somewhere. But there you see where this condition that Q restricted to L ought to be 0 comes from, because one of the terms is 0. So I can't do 0 just says something is 0. And then I need this square to be a Bullback, but the x prime term is 0. Yes, so really this Bullback materializes as a fiber sequence. And if you check what it materializes to, it does the following. So I'm reference to the statement that 0 to L to P is isomorphic via Q sharp to the dual of P to the dual of L to 0 in the exact sequence. That's the usual notion of the Grothendieck algebra that you would see. Okay, so here's another example. So suppose N is a closed and oriented manifold. Then we can do the following. You can look at cochains of N with coefficients in Z, and cochains of N with coefficients in Z, and then you all know, at least you know the cup product. The map from the homology of N to the two variable functions from the homology of N to the homology of M. And in fact, it refines as a map of this sort, which is in fact highly structured. So this is a commutative algebra in spectra, and this is just a multiplication map of this commutative algebra. So this is the multiplication. And so in particular, that materializes itself as being C2 equivariant for the flip action. So I'm allowed to say HC2 here. So I get a map to here, and then I can evaluate on the fundamental class of M. And that will get me a map to Z sitting in dimension minus N. Maybe I should fix the dimension. Okay. So that's the map that I have. Does that make sense? Oh, yes?
Yes.
What am I supposed to do S linearly?
Say it again.
Like, if I want to be over the sphere instead of Z, what do I replace this with?
You can do the same, but then you have, in order for it to be correct, you have to say framed, then you do everything over the sphere, or you parameterize over there.
Okay.
Then it works over the sphere. Yes. The orientation is the Z version of being framed. Okay, so you have this, and a map from something, like the orbits of something, to something with trivial action. That's the same thing as giving yourself a map QM in, I should say map over Z from cochains of M to Z M to Z sitting in the ring minus N HC2. This is an equivariant map to something which has the trivial action, just it's the same thing as a map from the orbits of that to Z minus M. And then I can say, well, okay, but this is just a shift that I pull out here. And then there's another exercise that I forgot to tell you, is that if you have any permission structure, comma, then you're also allowed to take loop spaces or suspensions pointwise of comma, shift that around. These are new Poincare structures where the duality just also gets shifted around. As well. So that's just something that you get. So this gives a Poincare object in the perfect category of Z with respect to omega n comma whatever I call it. Okay, so a closed manifold oriented gives rise to a symmetric type of Poincare object. And okay, just what it does. And likewise, a coordism gives you a coordism. If M prime includes into W and M includes into I, then I can look at cochains of M prime. Now that gives a map from cochains of W, where I can restrict along both of these inclusions. And the fact that the pushed forward fundamental classes agree, I prime, M prime is equal to I lower prime, will tell you that QM restricted to W is identified with Q of M prime restricted to W. And this you can infer from this formula somewhere. I really only evaluate on M if I know that the evaluation on M is the same as that on M prime. And these results. Okay, so that gives rise at least to the datum that I need to check whether something is a coordinate in the algebraic sense. So let's unravel what this means too. And we get, okay, so what is it we get? I guess something, okay, let me work out, hopefully, this square being the full deck is the same as saying the vertical fibers agree. So let's work out what the vertical fibers are. Here I have cochains of W sitting really, and here I have cochains of X prime. So if I'm lucky, then it gets out that you need to show that cochains of W and M prime are equivalent to an n plus 1-fold loop of chains of W. And the only thing confusing going on is that you have to understand that relative cohomology, relative things are defined as relative homology is a co-fiber, so relative cohomology is a fiber, and then you still dualize in these formulas, and you just get the most complicated thing is not getting confused about where it shifts what is a fiber and what is a co-fiber. But essentially, we're saying that the relative cohomology of the coordinate relative one end ought to be a shift of the relative homology to the other end, and that's what we learn as left shift direction. Okay, so this is correct. And maybe I should also say that the induced value you get is really given by tapping against the relative fundamental class and construction. But okay, I mean, the purpose of these lectures is not to explain the details of these constructions, but rather what are the constructions you can do and how do the algebraic notions relate to the geometric notions. And I'm saying this is implemented exactly as to reproduce Lefschetz duality for manifolds with boundary. Okay, so I have 7 minutes. So in these 7 minutes, I will want to categorify the notion of a coordinate. So the goal is going to be to, given the Poincare category, like this definition kind of looks the same as we did for Poincare objects. It consists of some object with an extra datum. It sounds like a Hermitian object, satisfying some property making it Poincare. So what we'll do is we'll try to construct a category in which the Poincare objects are exactly the coordinates. And that category is going to be sort of relevant for things that we do later. And then the plan for the next lecture would be to start with a summary of what are the categorical properties this category of Poincare categories enjoys. That's just going to be some painful statement to take in, but sometimes you have to do it. Okay, so here's the construction. Let's see about Poincare. Let's build a new category. I call it Q1, and also in the next lecture you'll see why it's called Q1. There's also a Qn for every n. Q1, and it consists of, I mean, it's supposed to be a Poincare category, so it consists of some category. I'll call it functors from the lambda 2 order to C. Okay, what is that? Those are just diagrams of this shape in C. So that's kind of what the shape of the coordinate is in our definition. And something I call my pop. And of course, cover cop is going to be what you think it is. I mean, if you just have to guess what the formula is from all the things I wrote down, it can only be this. We have to check that this is an effective Poincare structure, but okay, it's a concrete thing. And so the claim is this is the Poincare category. And let me say what the duality of cop is on such a thing, because I think that's always useful to work out. If you have a Poincare category, what is the duality that you get on it? And okay, I mean, it ought to do something on the outer terms. It's supposed to do what you think it does. Those are things that you can already dualize in C because you started off with a Poincare category. So this is something you can do, but now you have to produce something that maps to both. And you can't. There's only something that both of these maps to. You feel like you're out of luck, but you're not. You just take the full deck, and all of a sudden you constructed something that does map to both. That's not much for that. So that's the construction you do. And now let's just informally check what is the Poincare object in this category supposed to be. It's some object that's self-dual. That exactly says that x prime is equivalent to its dual, so likewise for x. So the outer terms are going to be Poincare duality objects, and the inner term is going to be equivalent to the fiber product. And unraveling that just means that this diagram is a full deck, this one, and that sort of was the definition of a Poincare. are exactly the coordinates in C. Okay, that's good. And let me just give notation. It's called MET. MET stands for metabolic categories. In algebra, a metabolic form is a form that has a Lagrangian. So metabolic forms ought to be coordinates to 0. So I just define that to be U1 of C copper, which is the kernel of the left boundary component that to C copper. I want to say if I have an object in here, I can look at the left boundary component, setting x prime x prime, and I can look at the kernel of this map, and then it will consist of things that look like this. Manifolds. Something you get. And so I'll finish by writing down a number of constructions you still have. So we get the following Poincare functors. So functors that are compatible with the Poincare structures and the dualities. So on the one hand side, I can take this Q1, CQ, and I can evaluate on both ends. So that's the left boundary and the right boundary component. That's something I have. And then I have the metabolic category inside. And there's another thing I can do. Maybe I can, yes, as in geometry, a closed manifold can be viewed as a coordinate from the empty set to the empty set. Yes? Right. If I have a D plus one-dimensional manifold, I can view it as a coordinate from the empty set to the empty set. And that ought to materialize itself somehow in this world, and it does so by saying that I can put C and omega comma into Met3 by sending an object X to the form that looks like this. And before in this example, you saw that the dimension of M, if I think geometrically, has something to do with shifting my comma around a bit. So it makes sense to think of the process of taking C omega comma as taking the Poincare objects, and there are some other Poincare objects that have one dimension higher in comparison to C. So they include into this metabolic category of this kind. And so here is the final exercise in this business, maybe to work out that you can do the following. You use this functor, but you shift it once. So you get this metabolic category of the shifted guy. And then the composite, which is the left boundary thing, is 0, yes, but the right boundary component is still interesting. Yes, the right boundary component of a metabolic thing just spits out the thing that you've equipped with an algorithm. And so that determines a map from the metabolic category of anything back to the category. So you can apply this to Met. And then this is sort of just the full subcategory, and the statements you can view Q1 inside the double metabolic category. And now use this, so I mean A, prove that this is a Grothendieck, and use this to describe Poincare objects of Q1, C, comma, in a different manner. Yes, so here we've said, I mean, the definition is made so that Poincare objects are coordinates. And this presentation will give you a different notion of, a different presentation of Poincare objects, because I told you this fun fact says that Poincare objects preserve limits. Yes, so if this is a Grothendieck, you apply Poincare objects, you get another Grothendieck diagram of Poincare objects. And then you can think, what are those? It's like a Poincare object in net, and a Poincare object in net, and a Poincare object here. And that's sort of interesting to work out what this is. And in our world, I'll maybe explain this to you if you want later, this is really sort of what we think of as the surgery equivalent. This is sort of at the heart of surgery theory. That the coordinate is the same thing as the trace of the surgery. This is sort of what this square, the algebraic interpretation, or the geometric interpretation of this square is sort of the fact that the coordinate is the same datum as performing surgery on one of the outputs. Input and then the output is the output of the surgery. Okay. finish here. Thank you very much.
So perhaps the benefit of those of us who are more geometrically minded. It's known in this step example, it's known that there are quantum grounded spaces that are not manifolds. So is there a nice example here in this category of a quantum object which doesn't come from manifold?
Yes, I mean you can just take the same thing works if I take a DB complex. But I assure you that there are also concrete objects that have nothing to do with geometry. And yes. I wanted to say there is a construction called the hyperbolic object on something that you can always do, but it's not completely unrelated to geometry. It's somehow hyperbolic form builds from any object something that has a concrete reality. But if you have like a finite complex, that's something that doesn't satisfy concrete reality, you can embed it into Euclidean space, take an along and take the dotted. That's related to this hyperbolic construction. So, I mean, yeah. But you can cook up things that are completely unrelated to it. But this construction doesn't need manifold, it just needs to have global concrete reality. Sorry, I just said manifold.
As expected.
Yes.
Is the resign diagram special, or you can like do something for general shapes of diagrams?
This one?
Like the upper legal part, where you have like this diagram. Yes.
Yes, I'll come to this in the beginning of the next lecture. I'll tell you now. The statement is that cut H is tensored and co-tensored over all small categories. So let me make sense of this. So this category has internal homs. This Hermitian category thing, so it's enriched over cat. So it makes sense to talk about co-tensors. And Hermitian categories are tensored and co-tensored over everything. But if you have a form rating and you tensor with something, it need not be concrete again. But it will be so if it's the base set of a finite complex, of which this is an example. But in general, this cut H has all the nice categorical properties, and you have to be a little bit careful. And so there are typically these tensors will not be concrete again unless you're just specific case. I'll start with that tomorrow, summarizing these properties.
Alright, so maybe let's just start to get going, and yeah, if you do not know the way this follows circles, then enough, and very well.
It's been recording at least the video. I hope the audio works, but I also recorded with my phone. So I'll do like a montage with my phone. I hope, like, okay.